Well, hello. I hope everyone is doing well. We are going to look at our final review for unit number 4. And if we recall, unit 4 was exponential growth, exponential decay, logarithmic functions, solving logarithmic equations, and several different types of word problems. So the first thing we're going to look at was our graphing of our exponential and logarithmic functions. So the first one we have is an exponential function. And if we recall, exponential functions have horizontal asymptotes. And that horizontal asymptote, if we remember, is going to be an equation. And that horizontal asymptote is going to be in the form of y equals. So with that, our horizontal asymptote is just right here. So our HA is at y equals 3. So if we're going to go ahead and graph that, 1, 2, 3. So there is approximately where our horizontal asymptote is going to be. And if we remember our exponential growth function, so this should have a nice little going upward type of graph. And with this, we're also going to have to find our domain and our range and our x and our y-intercepts. So let's go ahead and try to find our y-intercept. And if we recall with our y-intercept, the x value is 0. So this becomes that y equals e to the 0 plus 4 plus 3. So this becomes y equals e to the 4th plus 3. And that is just purely a calculator problem. So we're going to go ahead and take that out. Oops. And go back to our home screen. And we're going to have e to the 4th plus 3. And then we like to round things to the nearest hundredth. And remember, intercepts are ordered pairs. Intercepts are ordered pairs. So this becomes, so y equals, and that would be 57.60. And then so our intercept as an ordered pair would be 0, 57.60. So now we're going to go ahead and find our x-intercept. And with our x-intercept, the y value happens to be 0. So we have 0 equals e to the x plus 4 plus 3. So the first thing we're going to have to do is get our exponent by itself. So we're going to subtract 3 to both sides. So negative 3 equals e to the x plus 4. And then since this is an exponential equation, we're going to change it to a logarithmic equation. And our base is e. So this is log base e of negative 3 equals x plus 4. So x plus 4 equals the natural log of negative 3. Right here, this tells us we cannot do anything with this because we cannot take the log of a negative number. So this does not exist. So in this case, there is none. So when we're going to graph this, and this is all the way up here at 57.6, so way up here, we can kind of look in our calculator, but what's going to happen if we went e to the x plus 4 plus 3 and hit graph? Oops, you can't see. There's our nice little graph. Gonna cross that axis way, way up there. So it is going like so. And if we remember, our domain goes left to right. So domain negative infinity doesn't have any restrictions along that x. So it is negative infinity to positive infinity. Whereas our range, however, bottom to top, we don't have anything, we don't have anything. We're looking at that horizontal asymptote, and then that happens to be at 3, and then to positive infinity. So that is kind of our exponential equation. So if we looked at number 2, where we have our logarithmic equation, and if we remember log graphs, have vertical asymptotes, and they're going to be at x equals something. So if we're kind of looking at our equation right now, we have f of x equals the natural log of x minus 3 plus 2. In order for us to get that to be that x equals, remember we're going to set this portion right here equal to 0. So to get our vertical asymptote, it is that x minus 3 equals 0. So x equals 3. So there is our vertical asymptote. And remember, our basic graph for our logarithms are going to go up and then over, because exponential functions and logarithmic functions are inverses of each other, so they are going to go ahead and undo them. So if we're going to go ahead and find our y-intercept, with our y-intercept, what value happens to be 0 is the x, so we end up with y equals the natural log of 0 minus 3 plus 2. Y equals the natural log of negative 3 plus 2. And once again, we're going to find out we cannot do anything with this because we cannot take the log of that negative number. So in this case, there is no y-intercept. So now we're going to go ahead and find that x-intercept. And with that, the y value is 0. And I'm not going to have room if I do that right there. So I'm going to scooch that down here. And that y value happens to be 0. So 0 equals the natural log of x minus 3 plus 2. We're going to go ahead and subtract 2. So negative 2 equals the natural log of x minus 3. I like to rewrite this, as you know, as log base e. So negative 2 equals log base e of x minus 3. And now we are simply going to rewrite this as an exponential equation. What is my base? E. So e to the negative 2 equals x minus 3. So x equals e to the negative 2 plus 3. That is that exact answer. So we still do need to figure out what is that approximate, since we are looking for an intercept. So e to the negative 2 plus 3. And then that is then approximately to the nearest hundredth, 3.14. How crazy is that? 3.14, comma 0. I know it's not actually pi, but that's pretty darn close in that case. So now let's go ahead and double check this in our graph. So we have the natural log of x minus 3 plus 2. And when we graph this, remember these log graphs don't appear out of nowhere. That we do have to have an understanding that it is following this asymptote and then it is crossing and like so. So they do not appear out of nowhere. Don't forget that log graphs do continue on. It's one of those times where our calculator kind of sort of lies to us. Looking at our domain, left to right. So we don't have anything part of our graph, nothing, nothing, nothing. And the first midget we could have deals with that vertical asymptote. So that happens to be 3 to positive infinity, whereas our range, bottom to top, we have our graph, and we still have our graph. So it is negative infinity to positive infinity with that. Next thing that we did, we went ahead and solved some of our different types of equations. We have our logarithmic and we have our exponential equations. So kind of looking at the first 3 in this set, 3, 4, and 5, those are all different logarithmic equations. And we have log base 6 of x plus log base 6 of 2x plus 1 equals 1. In order for us to solve this, since we have to decide is there a log on one side or a log on both sides. Looking at this, there's only a log on one side. So we are going to go ahead and condense this down. So our first step is to rewrite this as log base 6 of x times 2x plus 1 equals 1. And now that this is condensed down, we're going to rewrite this as an exponential equation. What is our base with our log? It is 6. So this is 6 to the first equals x times 2x plus 1. So this is 6 equals 2x squared plus x, and I am getting really happy because guess what we're going to get to do? We're going to eventually get to factor this. So we have 0 equals 2x squared plus x minus 6. And we're going to go ahead and multiply first times last. So that happens to be negative 12. Two numbers multiplied together, that's negative 12, that add to be 1. So 4 and negative 3. So 0 equals 2x squared plus 4x minus 3x minus 6. And we are going to group our first two numbers together and group our last two numbers together. And we're going to factor out a 2x. And we have x plus 2. We are going to go ahead and factor out a negative 3. And we have x plus 2. So our factors are x plus 2 and 2x minus 3 equals 0. And then we're going to solve those. So we know x equals negative 2, x equals 3 halves. Remember with this, we do need to check to see, do we have extraneous solutions? So kind of looking, if I plugged in negative 2, log base 6 of negative 2, we can't do that. So that one is extraneous, and in this case, our only solution is 3 halves. Number 4 is a little bit easier. Still along those same lines, we have log base 2 of 2x minus 1 minus 3. We have to decide log on one side, log on both sides. And we're going to say, hey, we only have a log on one side. So we're going to rewrite this as an exponential equation. Our base is 2. So we've got 2 to the third equals 2x minus 1. 2 to the third is 8 equals 2x minus 1. Add 1 to both sides. So 9 equals 2x. Divide both sides by 2. So x equals 9 halves. And once again, This one will not have an extraneous solution, and we are finished with that problem. And then finally, the last one of our types of logarithmic equations, we have natural log of x plus 7 plus the natural log of x equals the natural log of 18. Once again, we have to decide, do we have a log on one side, log on both sides? We're going to notice we do happen to have a log on both sides, so that is going to be a little different, and it's actually a little bit easier to solve, but we do have to go ahead and condense this. So we have the natural log, and I'm going to go x times x plus 7 equals the natural log of 18. And since we have a log on both sides, we can use that little one-to-one property that simply states that this portion equals that portion. And I know you guys are thinking, oh my goodness, we're going to get to factor again. Because now we have x times x plus 7 equals 18, which is x squared plus 7x equals 18, and I bet you have smiles across your faces right now to see that. We're going to go ahead and subtract 18. So x squared plus 7x minus 18 equals 0. And we do get to factor. So what are two numbers multiplied together? That's negative 18 that add to be 7. Hopefully you're thinking that would be positive 9 and negative 2. So x plus 9, x minus 2 equals 0. So x equals negative 9, x equals 2, and always double check, do we have an extraneous solution? If we're to put negative 9 back up in here, negative 9 plus 7 gives us negative 2, and automatically that doesn't work. So our only answer in that case is 2. So now let's go ahead and look at solving our exponential equations. Done very similarly, because changing back and forth between logarithmic and exponentials are the ultimate super important thing for us. So looking at number 6, we have 4 times 5 to the x minus 3 equals 38. So we need to get our base by itself that has that exponent. So we're going to go ahead and divide both sides by 4. So we have 5 to the x minus 3 equals, and that reduces down to 19 halves. So now we're going to go ahead and change this to a logarithmic equation. And I'm going to ask, what is our base? And hopefully you're saying my base is 5. So this becomes log base 5 of 19 halves equals x minus 3. And we're going to go ahead and add 3 to both sides. So log base 5 of 19 halves plus 3 equals x. And that happens to be our exact answer. But we do need to go ahead and find our we do need to go ahead and find our approximate solution. Okay, sorry, I couldn't find my calculator there. And if we remember, we're going to go alpha window, and then that happens to be choice 5. So now we have log base 5 of, and then that would be 19 divided by 2. And then we can hit enter, or we can go ahead and go plus 3. And there is our approximate solution. And rounding to the nearest hundredth, that would then be approximately 4.4. Cool. So now, still along those lines, we've got 3 plus 4 times e to the x equals 21. So now we're going to go ahead and solve this one. Still getting that base by itself. First thing we're going to do is subtract 3. So we have 4 e to the x equals 18. Divide both sides by 4. So e to the x equals 9 halves. So what is our base? E. So log base e of 9 halves equals x. So that is ultimately the natural log of 9 halves equals x. Once again, that is our exact answer. And if we are wanting our approximate, we have the natural log of 9 halves, which is then rounding to the nearest hundredth, 1.5. So x is approximately 1.5. And we have our exact answer and we have our approximate answer. I forgot to circle them. So this would be our exact answer and that one is our approximate answer. So likewise on our very last one, we have 100 e to the 0.06 t equals 500. Same type of scenario, go ahead and divide both sides by 100. And so we have e to the 0.06 t equals 5. And we've got log base e of 5 equals 0.06 t. Change that to our natural log of 5 equals 0.06 t, and then divide. This is our exact answer, and if we wanted our approximate, we're going to go ahead and go natural log of 5 and then divide that by 0.06. So our approximate answer, rounding to the nearest hundredth, is then 26.82. Oops, there we go. And the last couple things we did, we had word problems. And if we recall, there were two main formulas that we used. We used PERT, A equals P e to the RT, and then we used A equals P times 1 plus R over N to the NT. This was if we compounded continuously, and this was just our compound interest formula. So ultimately we have to look at our problem when we're reading it and determine from there. So it says an investment of $10,000 averages an interest rate of 7.5%, which is invested in a stock-based mutual fund. Determine the doubling time if the determine the doubling time for this investment if the interest is compounded continuously. So ultimately, compounded continuously tells us we're using this formula. However, this is our ending amount, this is our starting amount, this is E, rate, and then time. It doesn't give us an ending amount, but it is saying we are doubling our money. So if we're starting off with $10,000, the ending amount is then $20,000. So 20,000 equals 10,000. E, our interest rate in this is 0.075, and we are solving for T. So we're going to go ahead and we have an exponential function or exponential equation. So we are going to go ahead and eventually change it to a logarithm. So we're going to divide both sides by 10,000. So 2 equals e to the 0.075 t. And once again, what is our base? E. So we have log base e of 2 equals 0.075 t. So 0.075 t equals the natural log of 2. And then we simply divide. So t is then approximately, and we're going to take our calculators and do the natural log of 2 divided by 0.075. And that is going to be then approximately 9.24 years. Then our next one says an investment of $3,000 averages an interest rate of 3.5% when invested in government bonds. If the interest is compounded continuously, so that is that PERT again, how long will it take for our investment to grow to $9,000? So now we have that PERT. And now we have an ending amount. Our ending amount is 9,000. Our starting amount was 3,000. E, we are solving for time again, but our interest rate is 0.035 t. And now we're going to go ahead and solve our exponential equation. Divide both sides by 3,000. So we have 3 equals e to the 0.035 t. And we're going to change this amazingly to a logarithm again. So we have log base e of 3 equals 0.035 t. 0.035 t equals the natural log of 3. And we're going to go ahead and divide both sides by 0.035. Plug that in our calculator. Plug that in our calculator. And so we've got the natural log of 3 divided by 0.035. And then that would take approximately 31.39 years. And we have 2 more problems to look at. The last two, number 11, says an investment of $20,000 averages an interest rate of 12.5% when invested for 7 years in a mutual fund. Determine the final balance in each of the following scenarios. And the only scenario is that the interest is compounded monthly. So that compounded monthly, remember we're going to use A equals P times 1 plus R over N raised to the N T. And that's really important because N is the number of times it's compounded, and monthly, remember, is there's 12 months in a year. So we want to know what is our ending amount. If our starting amount is $20,000, 1 plus our interest rate, in this case 0.125, then divided by 12 raised to the 12 times, in this case, 7. And this is kind of making sure we're plugging this in correctly. So we have 20,000, 1 plus, and then I like to do the little alpha y equals to make our fraction, just so we are making sure everything gets in there correctly. So 0.125 divided by 12 And then that is then raised to the 12 times 7. That's kind of the easiest way. And then we would notice that we end up with $47,760.86. So our account balance is $47,760.86. Uh-oh, looks like my pen is drying up. So, and then the last type of problem we did some population problems. And it says the population of a city is growing by, or given by P equals 250,000 e to the 0.012t, where t corresponds to the present day. According to this model, what will the population be in 20 years? This is just a plug it in type of problem. Sometimes, remember, we might have to solve for time, but ultimately that's just that compounded continuously problem again. So we have P equals 250,000 e to the 0.012, and in this case we're going to multiply it by 20 years. And we just want to know what our population is going to be, and we're going to plug it in. So 250,000 e, and then we're going to raise that to the 0.012 times, and in this case, 20. And when we're talking about people, remember we tend to round to the nearest whole person. Depending upon myself, I would accept 317,812 people, or if you had 317,813 people. So we would say P is, I would use my little approximate symbol, 317,812 people if we're using our rounding correctly. And that is it, ladies and gentlemen, for Unit 4. I was not planning on making a video for Unit 5 simply because that should be so fresh in what we've done. I will be hosting some Zoom sessions during the week, or starting May 1st-ish, maybe the following week when you get your actual review. Well, you have a great day. Have a good one. Bye-bye.